right, continuing our discussion of unit vectors. If we're in V2, there are two very special unit vectors that we have, and these are going to be the vectors that point in the directions of the positive x and the positive y axis. So if I take the unit vector, let's use a different color here. If I take the unit vector that points in the direction of the positive x-axis, we call that I, and its components are just 1, 0. I can pretty much see by inspection that that magnitude is just going to be 1. Okay. We call that I. If I prefer, I could write it as I hat because it's a unit vector. Sometimes students ask, is it wrong? Is it necessary to write the hat? Is it wrong not to? No, it's totally fine. I have to write a hat if I started with a vector v that wasn't a unit vector, and then I change it to get the normalized version of v. Then we call that v hat because it's different from the vector that I started with. If I start with I, it happens to have a magnitude of 1. If I normalize it, I would get I hat, but I hat is exactly the same as I because I wouldn't be changing it. It was already a unit vector. So you can call it I with a bar or I with a hat. Doesn't matter, but there should be a bar or a hat on it. Okay. I usually write the bar and the hat when I'm normalizing something because it was a vector, the bar to begin with, and then I'm normalizing it by writing the hat. Okay. All right, the vector that points in the positive y direction, we call that j, and of course, since that's going straight up, its components are just 0, 1. Okay. Now, if we're in 3 space, there are going to be 3 special unit vectors that we can work with. Okay. The vector that points in the direction of the positive x-axis, we're going to call that I, but now it's 1, 0, 0. Okay. This I is not the same as this I. This vector has 3 components, this vector has 2. You might say, well, why do we use the same name for them? Well, they're both the unit vector that point in the direction of the positive x-axis. And for any given problem, we're either going to be in 2 space or we're going to be in 3 space. It's going to be clear from the context what we mean. Okay? So it's just like if you've ever met somebody who had the same name as you. I've met other people named Carla. I never got confused and thought I was them. I always knew I was me. We just happened to have the same name. So if you're doing a problem and it's in 3 space and you write I, you have no reason to get confused and think that you're talking about this I because you're not working in 2 space. You're working in 3 space. Okay. All right, so that's our I. J is the vector that points in the direction of the positive y-axis, so that's going to be 0, 1, 0. And then K is the unit vector that points in the direction of the positive z-axis, so that would be 0, 0, 1. Okay. These unit vectors are kind of special because I can actually write any vector that I want to in 2 space or 3 space in terms of just these unit vectors. Let's take a look. Let's go back to our friend 3, negative 2. Okay. I claim that that's 3 i's minus 2 j's. I can write that as a sum of some i's and some j's. We would call this a linear combination of I and j. Okay. Let's see why that works. 3 copies of I would be 3 copies of 1, 0. Negative 2 copies of j would be negative 2 copies of 0, 1. Okay. Now, if I do the scalar multiplication, 3 copies of 1, 0 is just 3, 0. Negative 2 copies of 0, 1 is 0, negative 2. If I add these vectors together, 3i, minus 2j, I'm just going to get 3 plus 0, 0 minus 2, I'm going to get 3, negative 2. So I can write any vector in 2 space in component form using this bracket notation, or I can write it as a linear combination of some i's plus some j's. If I have a vector w in 3 space, let's just say I've got 4, -1, 5, that's going to be 4 copies of I minus 1 copy of j plus 5 copies of k. Okay. Now, if I had, let's say, we'll call it u. Let's say I've got u is 5, 2, 0. That's a vector in 3 space. U would be 5 copies of I plus 2 copies of j. Now I've got 0 copies of k. Okay. It's not necessary to write that I have 0 copies of k. Usually when I don't have anything, I don't bother to write plus nothing. Okay. So I could write this. Now I do need to be careful. If I have a vector like this where the z component is 0, as long as it's clear from the context that I'm working in 3 space, I would know that this is a vector that's in 3 space. If it's not clear from the context, I might prefer to use the bracket notation rather than the ijk notation if there happen to not be any k's. Okay, excellent. So that gives us some alternative notation. In general, I don't care how you write your vectors as long as you write them accurately. So I don't care whether you use the bracket notation or write things in terms of i's and j's and in 3 space k's. Okay, but you are responsible for understanding both types of notation. As you're going through the homework, you're going to see that sometimes your vectors are written in bracket notation, and sometimes your vectors are written in terms of i's and j's or i's and j's and k's. So you need to be able to interpret the problem. If it's given one way and you prefer another way, you can switch. I tend to prefer bracket notation, so I use that most of the time. And often if a problem is given to me using i's and j's, I might choose to convert it to bracket notation in order to do the work. That's just a matter of personal preference. Either notation is correct. Okay. I want to just do one example to show how unit vectors can be helpful for us. Let's suppose that I've got a point P, 2, 0, -1, and a point Q, 5, 2, 7. Okay. And I want to find the vector of length 10 that points in the same direction as PQ. So I'm not looking for a unit vector. I'm looking for a vector of length 10. The direction is going to be determined by the direction of PQ. Okay. I'm going to suggest that you pause the video, see if you can figure this out, and then tune back in and we'll work through it together. Welcome back. Okay. All right, what I'm going to do is, if the vector that I'm looking for, I'm going to just call that V, okay? I'm going to find 2 other vectors first. I'm going to find PQ. That's the vector that has the right direction, but presumably it has the wrong length. So I'm going to need to adjust the length. Now sometimes people say, well, let's just multiply it by 10. But if I multiply it by 10, I've made it 10 times longer than it is. If it wasn't length 1, if it was length 5, I've made its length 50. I haven't ended up with something whose length is 10 if it wasn't already a unit vector. So what I'm going to do is I'm going to normalize it. I'm going to find PQ hat. That's going to still have the right direction, but it's going to have a length of 1. Once I have a length of 1, the vector I'm looking for, which I said I was going to call V, that'll be just 10 copies of PQ hat. So if I'm going to scale a vector by a factor of 10, that just makes it 10 times longer than it was to begin with. If I normalize first so that I make the magnitude 1, then I can say, excellent, now when I scale by 10, I make the magnitude 10. All right, so let's calculate this. PQ, I want to remember I'm going from P to Q. So my components are going to be subtraction problems. I'm going to start my subtraction problems with my ending location. So it's going to be 5 minus 2, 2 minus 0, 7 minus a negative 1. So that's going to be 3, 2, 8. Okay. All right, let's clear a little bit of space. Let's calculate the magnitude of that. So the magnitude of PQ is going to be the square root of 3 squared is 9, plus 2 squared is 4, plus 8 squared is 64. So let's see, that's 64 plus 13. That's going to be the square root of 77. Okay. So PQ hat is going to be 1 over root 77 times 3, 2, 8. I'm going to go ahead and do the scalar multiplication. That's going to give me 3 over root 77, 2 over root 77, 8 over root 77. So now that's a unit vector that has the right direction. So now I can say V is going to be 10 copies of PQ hat. So that's 10 copies of 3 over root 77, 2 over root 77, 8 over root 77. And just doing that scalar multiplication is going to give me 30 over root 77, 20 over root 77, 80 over root 77. I'm going to stop there. I could certainly normalize or rationalize each of those components if I wanted to. In the interest of time, I think I'm going to stop here. But that just shows you how, even though my goal wasn't to end up with a unit vector, finding a unit vector as an intermediate step can often be very helpful.